Okay, hi everybody. I'm going to share my screen. Share. Okay, great. So today I'm going to do this actually every Thursday. So at this time, around 4, we usually have a meeting in our Discord group about this book. It's like a book club, but I'm thinking to make it even more general, where we can even alternate if you prefer. If you guys prefer, we can go scaled, one week. Then we can alternate and cover maybe papers about Bitcoin, like scientific papers about Bitcoin, different, or maybe different topics, scientific topics about data analysis, everything that is kind of relevant to Bitcoin, but going a little bit deeper for the people that are interested in math, in physics. It's supposed to be for everybody. It's not going to be super technical. Of course, when we read a paper, it will be a little bit more technical, but I will try to break it down for you, going through the ideas mostly without stopping too much in the math, and we can alternate like that. But it will be mostly like bringing the idea of science and to the world of Bitcoin and trying to learn different ideas and concepts in a different way. And by the way, this is a live conversation. So this is why I did it live, because I would like to interact with you. So at any time, feel free to ask questions. You can write them in the chat. I'm not sure if there is a way of making people talk. I will explore that in the future. That is one of the beautiful things about doing this on Discord, that actually people can ask a question by voice. But you can do it in the chat, and I will read your questions and try to. And you can do it anytime. It's more like a conversation. So I suggest you to read the book. Today we are going on chapter 3, the beginning of chapter 3, but you can catch up and read the other chapters, or you can also wait for me to actually. I probably will do it not live. I will do it because we already covered these topics, but I will do other videos covering the other chapters, and I will put them in a playlist called Scale, so you can find them there, all organized. And we can cover. And if you read the book, I will tell you ahead where I'm going, so you can kind of follow along. I will be probably also motivation. Some people sometimes need a little bit more motivation to read a book, and so if we have these weekly meetings, this could be a motivation for you to actually read the book and follow along. And you can ask a question. Don't feel you cannot answer questions if you didn't read the book, because also I'm trying to make these little presentations kind of independent. They are based on the book, but you can just ask questions about things we discuss. You don't have to read the book, but it's great if you can. Okay, so we can go and start. So first of all, I just posted. I love these. By the way, I have a physical copy. I love still physical books. I have the old versions. I have a physical copy. I have a Kindle version, and I have the audiobook, because the audiobook is also great. You can go somewhere and listen. And some of these books, they are so good, and they have covered so many concepts that it's actually a good thing to hear them. Maybe you can read them. There is a visual aspect. You can hold the book. That is really cool. There is still something good about smelling a book and holding it in your hands. Even if I am, that I want to become a cyborg, so I am all for technology, etc. But there is something fantastic about holding books. But you can hear it while you're working. So there is the audiobook. It's pretty good. They do have like figures, because there are a lot of figures, but I think the audiobook comes with the figures, so you can go back and check the figures. So it's cool. There are different ways of doing it. But in the in the jacket of a printed version, there are a lot of wonderful reviews about the book. But one of it I like best because all of them, maybe I need to start to put them in different videos so you can see the in the comments, right? In the description, the relevance of this topic that we are covering, that is the topic of scaling. And this is from Taleb, that probably you guys know. Unfortunately, he doesn't like Bitcoin. He used to like Bitcoin, and then he wrote this infamous paper against Bitcoin. But one day I will actually respond to his paper. One of the power lowers, AC Berger, that I work with, he actually has an article where he responds. If you guys want, I can put a link there, so you can read his response to the black paper. Instead, it's called the black paper instead of being the white paper. But his arguments are not very good. It's good that he's introducing some concept that could be useful, but his conclusions are not good. But in general, he's very good. He studied math, and then he applied math to options. I have his option book that is amazing. One day maybe we can review it together, because I want to dedicate this Thursday meeting to go deeper in books, articles, different books that are relevant, and maybe we can study his book at a certain point. But he has this wonderful quote that is, and the quote goes like this. It says, "Each human should learn to read, write, and count." Okay, of course, right? And those who know how to count should learn scalability. So this concept of scalability, right, that we say is very relevant to understand Bitcoin. Scaling is the most important. Listen to this. Scaling is the most important, yet most hidden and rarely discussed attribute. It's very strange because, as a physicist, we cover this topic of scale, and it becomes almost like second nature. And then interacting with the public, I can see that many people don't even know the name. Some people are even put off by this. When I say scaling variance, it seems like a fancy term, right? And people get turned off, but it's not really a difficult concept. Maybe it's difficult to try to make it like second nature and start to see the world, but this is one of the things that this book really does. It helps you to see the world through these eyes of scaling. But even, of course, we are Bitcoiner, most of us. Maybe some people want to learn about this topic, and they are no Bitcoiners, and they are coming here to learn about scale, etc. But we say that it's very relevant to understand Bitcoin, and little by little we can introduce why, what is a connection, etc. But scale, it's one of these things that I think everybody knew about it, but then interacting with the public, I found out no, it doesn't. It's not like that. Many people don't know about it, and I was very surprised. But hopefully, by working on this book, it will start to become much more natural for everybody to think it their stem. And then you will apply to Bitcoin, and you will understand why Bitcoin is behaving in a certain way, and it will give you a different light to understand Bitcoin. That is my goal with this. And they say scaling is the most important yet most hidden and rarely discussed attribute, right? Rarely discussed. Without understanding it, one cannot possibly understand the world, right? It seems so much, right, about this, like it's a critical understanding, and so many people are completely, they are ignorant about it. They don't know about it, and so yeah, let's go deep and try to understand it, because beyond Bitcoin, and it's amazing that Bitcoin has these scaling properties, it's also important to understand the world. You will understand many different phenomena around you by opening your eyes and your mind to this new concept of scaling. Okay, or maybe it's not completely new, but you never thought it in this way, in these particular terms, like the idea of scale itself. Okay, so first of all, here is an example of why scaling is important, right? And in the book, they started to describe life, because this chapter is mostly about life, how life is a phenomena that can be also understood mathematically. Because I was discussing today, by the way, I talked with his name is Theodore, and he's a physicist. He's a very young physicist. He graduated from Oxford, and he had to build an entire CAT scan, by himself. Can you imagine? That was his dissertation. It's not like some of the silly I don't want to attack people from, the humanistic field, but imagine your dissertation is to build a CAT scan. Of course, the university pay for the components, and he had to do it all by himself, like building this thing. But so this guy knows his stuff, and is a good engineer beside being a good physicist, because CAT scan are all based on physics. The physicists invent CAT scan. We invent almost everything, and then the engineers make it better, more functional. They improve it, but a lot of things around us were invented by physicists. And he was telling me, Giovanni, any physicist, any mathematician, it looks at what you did, it downloads the data, you do it yourself, and it's obvious. It's a power law. There is no doubt about it. I know. So far, I didn't have one single professional that came to me and say, well, look, you did something stupid, and say that. No, these are trolls. So, once in a while, you find somebody that maybe has a different background, a computer scientist, they don't do the things we do, etc. But there is consensus on this. And in physics, our way of looking at physics is looking at the entire world, right? So we try to understand everything, like if it was one big single phenomena. One of the holy grails of physics is to find one single equation that we can write on a t-shirt. So if you think it's silly to try to describe Bitcoin with one single equation, imagine the dream of physicists that to find one single equation that describe the entire universe. Maybe it's not just one, maybe a set of equations that work together, but something that is so small that you can write it on a t-shirt. But also we go from the physical world. We want also to understand life. So more and more physicists are actually exploring life. And in the book, they make a big deal that we can also apply physics to social phenomena. And that is the relevance for Bitcoin, because I still hear people coming to my ex and say, oh, you should not apply physics to social phenomena. Why not? People have done it and have done it successfully. Everything is physics. Everything is physics. It's just that we started with the simplest thing, the quote unquote physical world, but stones falling, etc. And then we move it. We recently, like in the last 100 years or more, we started to study life, and now we want also to study social phenomena, and we are very successful in doing that. And of course, it's more and more complicated, but physics wants to study everything. Now, life, or what concerns life in itself, it's from, if you want to look at it from this scale point of view, is really cool, because there are so many different sizes, right? So scale is all about this idea of changing order of magnitude. And what is an order of magnitude? It's this idea of going a factor of 10 up, right? We could go a factor of 5, but in general, right, we are used to 10, because 10, we have 10 fingers, right? Where that 10 come from? If we had 12 fingers, probably we'll create a system based on 12 fingers, 12 numbers. But we are humans, we have 10 fingers. And so we created this numerical system that goes 10, 10, 10, 10, right? Multiples of 10. So every time you change a multiple, you change perspective, right? You look at things much bigger, and then you're trying to see what is common in this huge big range of things. Is there some kind of commonality between all these different sizes, or do things change? Like for example, when we go from the atomic world to the world of common objects, right? The humans are used to deal with. And by the way, I don't know if it is a coincidence, or is more like we need to be there to be who we are, because we're kind of in the middle, right? And we are in the middle of this huge big range, both in terms of life, but also in terms of the universe itself, right? If you're looking at all the different scales involved in the universe, we are man is kind of the measure of everything, right? It is what we said in the Renaissance. Man is the measure of everything, because we kind of are in the middle. We are not too small, because probably if we were too small, predators will have eaten, and we will not have been the dominant species. If we were too big, we will use too much resources. So we are in the middle. That is a good thing. That is another idea that if you're starting to think about that, it's really actually interesting, right? It's one of these concepts that maybe you never thought about it. Sorry, the phone is going on. You never thought about it, and now you start to think because of this scaling. And so if we focus, first of all, I wanted to tell you about a scientific notation that it's very useful to use in science. This is why many of my graphs they show this scientific notation, because I know you like, some people like 10,000, like 10 comma, and like all these zeros, but I get it, and I will try to do more graphs like that. But there is a reason why we use a scientific notation. It's because we want to emphasize the scale, and so it's not very difficult. Look, if I write 1/100, it's 10 to the minus 2, because it means 1/100, and that minus 2 means you're dividing, and you write down the number of zeros involved, right? In this case, 2. 1/10 is 10 to the minus 1, and you write it in this way. And then 10 to the 0 is always 1, and 10 to the 1 is 10, 100, and so on. You can see, right? 1 billion. You see, imagine, like, for example, if I do graphs of hash rate, right? We are starting to talk about enormous quantity of hash rate. Imagine if I had to write all the numbers, right? Some of these numbers, like 10 to the 21, right? Okay, you could use B and T, meaning exa, and trillions and billions, but imagine if I had to write all the zeros, it would be crazy. This is why we like the scientific notation, because it's compact. I can write billion as 10 to the 9. I can write trillion as 10 to the 12. It takes some time, but it's one of these things that is worthwhile to learn. And so Bitcoin range, I was saying, just to give you an idea of the range that is involved in Bitcoin, we go from 10 to the minus 4, because the first transaction was $1 for 5,000. And when you do this order of magnitude, they always round to the closest 10. So we can say that it was 1/10,000 roughly. And so that will be 10 to minus 4, right? And in 2009. And now we are close. Again, if we round it up to the closest number, that is 100,000. And 100,000 is written as 10 to the 5. So that will be 9 order of magnitude. That is crazy. It's a really crazy, enormous, crazy range. Hi, Sander, say that he's here. If everybody wants to tell me your name, that will be great, even if you don't have questions, if you feel like. Yeah, for what concern life, we represented here. They say, okay, so look, what is the range of possible range that we deal with life? And so we start with molecule. But many people will think, wait a second, what molecule has anything to do with life? Well, because life is about these molecules. They come together, they interact together. So if you wanted to pinpoint, the beginning of at least the components that are necessary to create life. I don't know why it does this weird thing that at a certain point the image is gone. Let's go back to it. Maybe if I click on it, just give me a second. All right, maybe I need to click again. Yeah, now you see it. So they start with, in the book, we start with molecules, because maybe it's like one of the components that is necessary for life. And then, they go to these other things like amino acids. So, we start to have a bigger thing. So the molecule, see here, we use this nanometer, right? So 0.1 nanometer. Nano means 10 to the minus 9, right? It's like a billions, but for small quantity. 10 to the 9 is a billion, and 10 to the minus 9 is a nanometer. In this case, it's 1/10 of a nanometer, because more or less an atom, the radius of an atom, as a physicist, we remember by heart all these scales. 10 to the minus 10 is roughly the size of an atom. The nucleus, and here they don't mention nucleus. Anybody, if you want to, I'm going to ask some questions. Don't ever feel I'm pressuring you to answer, but you get extra point if you answer. Why they don't mention nuclei? Why is nuclei are about actually 100,000 times smaller than atom? Is one of the analogy that sometimes we use is like a little baseball in the center of a stadium, and then where the people are is where the electron is, and the nucleus is that little thing in that little ball. So it's 100,000 smaller than the stadium. It's very, very small, very little ball. And everything in between, it's nothing. It's emptiness. The universe is mostly empty. We don't mention nuclei here because there are very rare phenomena where events and laws that have to do with nuclear physics, right? So radioactivity and other things like that. They have a relevance for life in certain cases, because maybe like background. One of the reasons why there is mutations is because there is this underground. There is this background radiation in the world, and some of it is created by radioactive material that you have in rocks. If you have a shit rock in your house, and by the way, now that they say shit, like if it was, I don't know how to pronounce that long key, like shit, but you know what I mean. If you have like these panels, right, this in your house, they contain a lot of radioactive material, unfortunately. Not to the point that it's dangerous, but there is some background radioactivity in your house due to these materials inside your walls. But they actually, if there is a little bit in the background, they can help with mutations, with genetic mutations. That is part of a life process, right? Anyway, but most of the time, nuclei are not important for life. This life starts to be relevant at the level of atoms. And so this is why we have atoms. When they go, we have more larger structures. And so we look at things like amino acids. And these are about, they go up by one order of magnitude. They are about 10 times bigger, right? So 1 nanometer. There is all these, like, it's almost like a science fiction idea right now, but people say that one day we will have nanotechnology, right? Maybe you heard this term. What do they mean? It's technology that work at this level, at the level of things like amino acid, DNA, etc. Atoms are 1/10 smaller than that. But if we had machines that were made of several atoms, so not exactly one atom, but many atoms, but not too many, and they are at this particular size, then we could build things from the bottom up, right? We could build a car that is made of atoms that we put together one by one, molecule one by one, and doing it in this way will be very, very strong materials, right? This is why sometimes you see these science fiction movies, right? Or like Marvel or whatever, where they show people with nanotech armor or something like that, because the idea will be, if you can build things atom by atom or molecule by molecule, you do it in a way where basically there are not imperfections. So many materials break, even the strongest material like steel or whatever, they break because they have a little imperfection, and when you put a lot of pressure, or like something explodes nearby, that little imperfection create cracks, and then the material breaks. If you could build something that doesn't have any imperfection, it will be very, very strong. So this is one of this idea. But also, we could maybe fight viruses. We could kill them sending these little nanobots, and instead of having medicine, you will take that will be something that probably even the people from that don't like vaccines will be okay. Of course, they will have conspiracy theories saying, okay, they are injecting little bot inside us, who knows what they do. But there is always that possibility. We need to make sure that people are good agents, they don't do stupid things. But that is a possibility, right? If we could develop a technology where it is ethical and nobody's manipulating us, it will be amazing. We could uh, heal people from all kinds of illnesses, cancer, and viruses, kill them directly without affecting the other cells. And so, yeah, right, we go up another order of magnitude. We start to go in the realm of protein and ribosome, all these more complicated structures. DNA is kind of in between. And then we have viruses that are very small in comparison with other things, and in this case, 100 times the size of an atom. Uh, no, sorry, if it is the atom is 10 to the minus 10, right? And so more like 1,000 times. So, well, some viruses are smaller than 100 nanometers. And so, they are very, very small. In fact, they are so small and they are so primitive in what they do that there is this debate: are they actually part of life, right? If I had to draw a line and say, yeah, these are the component of life, or things that are kind of in between the life realm and things that are definitely life, where should I draw the line? And some people, it's kind of fuzzy. Some people say, maybe viruses, we should include viruses. Some people say maybe not. Right now, I think most biologists say not, that viruses are kind of like a little code that kind of seems alive, but is not really alive. And then as you go up here, these are all life things, that we will recognize, like, for example, bacteria and blood cells. This is how we go up by factor of 10, right? This is why all different type of scales. These are the concept of scales going up by a factor of 10. 1, 10, 100, right? Bigger and bigger things. And then, so these are some of the largest unicellular organisms. So somehow, life started as little cells, and these cells are, 100 nanometers. So basically, it's 100 times nano. That means, you see, this is why it's useful to have a scientific connotation, because I can do it in my head. I know that nano is 10 to the minus 9. I multiply by 100. I know that I have to subtract 2 zeros. It's about 10 to the minus 7 meters. And so a micro, I'm sorry, here is nano, and they say I made a mistake. Forgive me for that. You see this mu, actually, that mu means micro. So somebody should have corrected me. Micro means a millionth. So we are going from things that are nano, that are 10 to the minus 9, to things, these are much larger, are things that are micro, right? Micrometer. So micrometer means a millionth, 1 million, 10 to the minus 6. So 10 to the minus 6, these are structures, and we go 10 times higher. And by the time we go to 100 micrometers, so that will be 10 to the minus 6 multiplied by 100, it's 10 to the minus 4, right? So it's a little bit smaller, 10 times smaller than a millimeter, because a millimeter is 1,000th of a meter. So 1 millimeter is where kind of our eyes can start to see all these. This is how they have different type of instrument to actually see things. You would need a light microscope, X-rays. You would need an electron microscope. Different type of instruments that allow us to see things like these that are so small. And by the time we arrive to a millimeter, we start to see things. And also, what is interesting here, we could put we could put a line, say, okay, above this line we have life, and we could put another line here, say, above here we have multicellular life. So somehow, at a certain point, life, and this will be interesting as we discover lives in other planets and things like that. I think, for example, my opinion on these, and these are opinion, of course, are opinion based on the things I know about the universe. There was a time when I was actually teaching astrobiology. That was really fun, trying to understand the possibility of life on other planets. And we were discussing, in the class, how likely life is. And I think it's bacterial life is probably likely. It's not easy to have life in the first place. You have to have a lot of conditions. But given we have so many planets, probably we should find eventually, right, when we explore all these planets, we have spaceships to do that, etc. We will find a lot of evidence for microbial life or unicellular life. It should be relatively common, not so easy, but it should be quite common. But already going from just one cell type of life to many cells, right, is going to be much more difficult. Somehow on Earth, there was a time when that happened, and the cells, of course, it's not something that they decide because they had a mind or a brain to decide that, but somehow they organize themselves where they could specialize, right? You do this, I do that, you process the food, I make sure the fluid gets distributed everywhere in our organism. So it's very fascinating that these cells decided to come together. They did this different experiments under certain conditions. Maybe there is not much food available, so instead of competing, they need to work together. Maybe there are predators that are eating. So it's a very interesting topic that people explore. We don't know all the details, but somehow life decided to start to organize itself in terms of many cells, right, coming together, and they created all these beautiful, amazing structures, that are all the different plants and animals that we see all around us, all the diversity of life. It is unbelievable. That is one of the most fascinating, beautiful things. And somewhere there is us, right? So they go from things that are all the way to millimeters to 10 meters, like a huge big elephant or even a whale. And you see, we are there, right? Because 1 meter is basically 1 yard, like very tall people are about 2 meters. I don't think there's any humans is 3 meters. Maybe there is, I don't know, there is an exception or whatever, but it's about few, right? Few, or maybe there are very short humans that are less than a meter, but the range is that 1 meter is there. This is where we are. And there is all this incredible variation. So this is one of the, even just recognizing that there are all these different phenomena and they are distributed over many, many, many scales. It's an amazing thing, and it gives you an insight. You see, with one single picture, you can see the diversity of all these phenomena, all these things that are necessary for life, all the way to actually how these things come together and organize themselves to create these complex structures that we call animals and plants and things like that. Now, if you want to go and look at a bigger picture and see, say, okay, this is the range of scales. In this case, it was size, but this is in the book too. They talk about mass, so you can look at different quantity, right? So you can look at, like when we study Bitcoin, we look at the price, we look at hash rate, and all of these things, hash rate, addresses, price, they are all scale up in a very organized fashion. That is why we talk about this scale in the context of Bitcoin, because Bitcoin does the same thing. It scales up. It goes from very small little thing, like the price, a fraction of a dollar, all the way to 100,000. The hash rate from being small quantity all the way to be enormous. Right now we're talking about 10 to the 20, an enormous quantity like that. That for hash rate, right, where you need to use scientific notation to even write it down, and so it's a scaling phenomenon. It's a scaling phenomenon, Bitcoin, and so it's interesting to see other things that scale up. In fact, the entire universe has many, many different scales, and if you think in terms of weight, for example, the weight of an electron is 10 to the minus 30 kilograms. Basically means 0 with 29 zeros. whatever that is, you will have to use. I saw one time. I don't know if you ever saw this Ali G show. That comedian, and he was making a presentation for Trump, I think, or something, and he was trying to tell him how many people like ice cream, and he wrote this huge big number, like this old-fashioned um, presentation where you have like this kind of paper, right? Huge big paper where you write down stuff, right? And the other say the number is so big that I had to write it down like this, vertically. Of course, it was funny, right? It's a silly thing, but yeah, we will have to use a very long piece of paper to write this thing. Many zero, so many zero. This is why we like the scientific notation, because it's so easy to write it down, right? Like 10 to the minus 30. It means 0 with 29 and then 1 in the end. That is the weight of an electron. Very, very, very small, very light thing. And it's 1,000 times bigger by the time you go to an hydrogen atom. 10,000, sorry, 1,000 times bigger. And then, there are different molecules. We are going higher here in terms of the things we see. This is already 100,000 times bigger, right? A change in 5, right? Between 27, minus 27, and 22. So the number of 0 tells you how big is the difference. And by the time we go to things like, here we mentioned mitochondria, so components of a cell, we are going up by a huge factor. So, for example, going from here to there is about 6, right? So that will be 1,000,000 times bigger in mass. And a bacterium will be 1,000 times bigger than the mitochondria, that is basically a component, right, of a cell. So, by the time you go from here to there, you can see how many orders of magnitude. Then, a general, so this will be a bacterium. So, it's a single organism or unicellular single, but this is probably the cell of a complex organism like us that are bigger themselves, so 100 times bigger. And the amoeba, the bee, by the time you go to a bee, we are talking about many, many, many cells, right? There are millions of cells making a bee. And then us, right? Again, humans are about 100. So you could say, again, we are kind of not exactly in the middle, but we are not too small, not too big. We are kind of there, right? In this, the electron is 10 to minus 30. When you start to talk about the sun, for example, it's kind of curious, right? Minus 30, the electron, the sun is 10 to the 30 kilograms. So a range of 60 order of magnitude going from the electron. That is unbelievable. I don't even know if there is a word for something that has 60 zeros, right? If you take the ratio between these two. When you take the ratio, in this case, you subtract, so it's 10 to the 30 minus 30, so you sum, right? So 60. So a range of 60. The Earth is over there, right? So big animals will be about 1,000 times bigger than, in terms of weight, bigger than a human, right? A whale. But by the see, it's an enormous gap here by the time you go to things like the Earth itself. And the sun is about 1,000,000 times than the Earth. You can fit 1,000,000 Earth inside the sun. And then if you go to things like black holes are like different ranges, but many times the black hole is eating up all these stars, right? It's eating many, many stars as it leaves. And so it can bring, this will be a black hole that is basically 1,000,000 times the mass of the sun. And then if you look at all the stars, there are basically 100 billion stars in the galaxies. You will get this enormous number, 10 to the 42, right? You can see the difference here is 12. So it's actually, 100 billion, right? 100 billion will be, if you take the ratio between these two, will give me 100 billions as a result, the difference between these two. So it's really cool, right? Again, I don't know if you ever consider these, or there are like sometimes it was very popular in the 80s. We had these videos where they kind of zoom in somebody, like I think it was a lady in a park somewhere, and she was eating a sandwich or something, and we were zooming in and showing the different the atom, and then it was going up the cells, the planet, and we had a video. Maybe if I find it, I will put it in the links in the description, so you can actually watch it, because it's really cool, animation, and it gives you a completely different perspective. I think every single human being should go through an exercise like this at least once in their life and say, do I understand the different range of existence, right? How big this range is. And this is exactly an exercise in scaling. And this is why Taleb was making a big deal. This is just the beginning, right? In understanding how relevant scale is. But even just this, having this understanding of a universe, looking at different weight, etc. I don't know if I teach this in class, in schools. I think very probably some of the best teachers maybe they do that, or even have the understanding, because many teachers in high school, they were not doing very well in college. I thought many of them they were there because they wanted to get a degree and then get a job, but they don't have the passion, the enthusiasm, etc. But to me, just looking at this, it's like mind-boggling, right? And it's very difficult to even comprehend what the heck it means, a galaxy made of 100 billion stars, right? And all the huge big distances between the stars. You look at a picture and try to absorb it, but can you imagine? I did one time an exercise with the students just to give you, when I was teaching physics, just to give you a feeling, right? Because many times we want to have like a direct experience of these kind of things. For example, do you know how big of a number you will get if, imagine you count every second, right? And we try to simplify things, because if I start to say, okay, you spend 12 hours sleeping and 8 hours sleeping and everything else, you just count, all of your day. When people say, well, but you have to stop eating it. I'm trying to simplify, right? Because it still gives us feelings. So imagine, to make it simple, you count night and day, right? Even during the night, you count. And we could correct for that. It will be basically almost like 1/3 less. But let's make it simple, where you always count, right? You take some medicine that doesn't make you sleep, and you count one every second, right? So they taught us when I was in the military that if you say 1,000, that is kind of like a second. So 1,001, 1,002, 1,003, it takes about a second before you say 1,000. I don't know if it is true, but something like that. Or you take a clock and you count, 1 second, 2 seconds, 3 seconds, so on. By the end of the year, right, and you can do it in your calculator. You can do 24 times 60, right, because there are 24 hours, right? You can do it together, 24 times 60, because there are 60 minutes in an hour, right? 24 hours, and you multiply by 60, that is 60 seconds in a minute. I know already it's something on the like 10 to the 7. So basically, so it's 86,400. Let's round it up to 100,000, right? So that will be, that will be 1 day. So let's multiply that for 365. That is 1 year, right? And if I divide that number by 1,000,000, because we want to know how many millions seconds there are, let's divide that by 1,000,000. That is 10 to the 6. I'm doing it on my calculator. It gives us 31. So it's about on the order of 10 million, right? Because we round always to the closest 10. So if you count it whole the year, day and night, by the time the year is over, you are only at 10 million. So to go to a billion, that is 1,000 times more, you will need 100 years. So it will take you 100 years of this continuous counting over and over again, right, all day long, to reach a billion. This is how big a billion is, right? And when you start to talk about things like, imagine talking things like 10 to the 42. How many years is that? Millions and millions of years, right? So it's incredible. It's incredible how big these things are, right? Many people don't realize a billion is so, because even with the economy, we just gave $10 billion, to this nation or whatever. And they don't realize, it will take you, if I take a billion, it takes you 100 years to count. 10 billions will take you 1,000 years to count, right? It's crazy. It's crazy how big these numbers are. And, this is the idea of scaling, that we are scaling up, and the universe is made of these orders of magnitude. So it's a very powerful way of looking at the universe once you understand it. And then, the next slide is, so this is from the book. We introduce this slide. We talk about the variety of life. And then, just mention some of these things, the ratios between these quantities, how many stars there are. It's very nice to use the scientific notation because it's relatively simple to do ratios, right? For example, you see, if I want to say if I look at the galaxy and I look at the Earth, how many times the galaxy is bigger relatively to the Earth in mass, right? I take the exponent, right? We say it's 42 kilograms, and then I subtract it. You see how easy it is? Because this is why we like it. Because this is easy, I can even do it in my head, right? 42 minus 24, and I get 18. And 18, you can think, that is the other thing about the scientific notation. I can do it in my head, but I know it's a 9, that is a billion. And if I do a billion, a billion, right? 1 billion of billions, right? Then that is 10 to the 18. So I can say it's a billion of a billion, right? Is 10 to the 18. And so it's actually a good way to learn how to use this scientific notation when you're thinking about scales. And you can look at 10 to the 30, that is the mass of the sun. The Earth is 10 to the 24, right? So if you take the difference between these two, you get 6, that is a million. So basically the sun is 1,000,000 times bigger than the Earth. And so you see this graph shows we kind of like in the middle, right? We are not as small as the atoms or the molecules of the bacteria, etc. And we are not as big as the galaxy. So it's not roughly exactly the middle. Like it's such an interesting that the sun is 10 to the 30 and the electron is 10 to the minus 30, and we are smack in the middle of these two. But by the time you go to galaxy, etc., you get bigger things. But still, right? It's kind of interesting that we are there. So the idea, the book also, the next things that he says that the building blocks are the same, and this is why they mention it in the beginning. This is why it was interesting whenever we talk about the phenomenon of life, we want to include the building blocks, that are these basically atoms, and but then the atoms organize themselves and they form these organic molecules, these amino acids, right? Like all life is made of these amino acids. So like one of the requirements to create life. And then you have these there is some discussions if we really need things like DNA. Is DNA, like for example, if we ever discover life in other planets, that will be one of the first things we want to ask. Do they have a DNA? Do they organize information? Because probably life has always to do with the transfer of information, right? The parents want to, even if it is a simple cell, right? The cell breaks down and transmit the genetic information. They don't have genes, but the information to the other cell, right? The simplest form of life don't have genes. Genes is something that comes later, right? That there is more information there, and how it organized, etc. But the DNA is one of the first things that allowed us to, replicate life over and over again, almost like if it was like a little code, right? Do they have two strains? Is it something that is always like that? Even in other planets, so maybe we have 3 strains, or maybe they have some other mechanism to transfer information. That will be one of the first interesting things to ask. But at least on Earth, all these components proteins, amino acid, DNA are basically a fundamental part of life. They have the same. And in this huge, big range of life, we have the building blocks, but then how the life is expressed, the different type of shapes and forms and functions, they are so different. That is a very amazing thing. Um, and one of the so again, when I was teaching this class, it was really cool because it gave this astrobiology class. It kind of brings things in a different context. Like, for example, if we want to say, okay, what are the characteristics of life, right? Besides the size, but if I had to identify what makes life, right? Thing is alive. This thing is not alive. Also, because if you see how changing perspective sometimes allows you to think or answer questions in a different way. Like if you were trying to put it in the context of not just life on Earth and you wanted to understand life in other planets, that would be a really cool question, right? If I find this thing that looks like life, is it really life, right, in another planet? Even if maybe behaves in a very different way from life that I know. How will I know, right? It is something that I could call alive. But one of the things that we can say about life that makes it different from other processes that we study is that it's using energy. And most of the time, there are some life forms that actually take energy from rocks. They eat rocks, or they use even, I think there is a one crazy case where they use even, if I remember well, even nuclear energy, so like really crazy, like this very extreme type of life that actually scientists study because they could be type of lives that we find in some absurd planet, where radiation is so high and maybe, they live under the rocks, to protect them from the radiation. And they are like this, so they are called extremophiles. There are some life forms that actually like these extreme cases because they don't have a lot of competition. They specialize to live in these very crazy environments, and they don't have competition. Like if you go to Yellowstone Park, there are some crazy life forms that live even in these acid pools. Like we have some pool of water that is very acid, very hot, and they live there. Like if you go there, you get melted. But and some people sometimes fall inside the pool and they die. But there are some organisms that live there, believe it or not, because they got specialized. But in general, it's this idea, basically the idea that is one of the things that you could say in general about life. It is very unique. There are other things because it's not like a unique way of identify life, but it's for sure a component where you take energy and then you use energy to organize this life form. And basically you go against one of the most fundamental principle in life, right? You know what I'm talking about? What is one of the most, not in life but in the universe, what is um, this principle that I have in mind that right now we don't know how to defeat. By the way, it's like one of the things that it's a kind of an obstacle for humanity and for everything, right? It's the fact that the energy goes from organized forms to disorder, right? The universe tends to go from order to disorder. There are different names for that. We call it entropy, but also, it's related to the second law, thermodynamics. But life does the opposite, right? It takes energy, and then through some process, it increases the order inside the organism. Now, that it doesn't really goes against the laws of physics. It's kind of, you know, um, a trick in a way, if you want to call it, but also it's basically you can do it locally, right? Inside the organism, we can increase order. We pay the price that we dump things like heat, for example, the heat the animal produce or the waste that the animal produce, we dump it in the environment. So we still increase the total entropy of the universe, but at least locally we increase order. And this is why you can have all the beautiful things associated with life, different complex systems, different behaviors, right? You can create the brain, organs, all these things, because you increase the order, the complexity of the organism. And it's amazing, right? If you look at these and you're thinking it's all these processes through evolution, through basically machines. They're like little machines, these cells and all the things that happen. And all this is done through millions and billions of years of evolution. It's mind-boggling, mind-boggling. It's like, and I understand, how many people think, or even before science this started to study these things, people thought that there was some creator, and they did. I don't want to debate there is a creator or no, because it's so personal. Everybody has his own life history and all beliefs, so I don't want to. I have mine, but if you want, I can share. But right now, I'm not going against. But it doesn't have to be in contradiction with your belief. Like, even if, let's say, there was a God, he decided to make it in this way, with this, like all these mechanisms. But it's another way of expressing creativity, right? But it's all done through processes and steps, right? He didn't simply snap his finger and made it happen, right? So I don't want to criticize your belief and your understanding of the universe, but right now, through science, we are finding out that it took millions and billions of years, but they are all explainable by science. There is nowhere we find, there is this step that we cannot figure out. Sometimes it's so complex and so difficult that it takes years and years, but every time we try, we find the missing pieces, right? And we are doing more and more and more progress in understanding these things. And we can end in a couple of minutes, because I want to keep these little lectures or discussions within 1 hour. And so this is what Jeffrey, the author of a book, right, G.West, discusses here. He says, understanding more generally the emergence of complexity from simplicity, right? Because we start with very simple things, and life is all about creating more and more complex forms. An essential characteristic of adaptive evolutive system is one of the founding cornerstone of a science of complexity. And this science of complexity has very much to do with this idea of scaling, where we are going when we are going to study, for example, society and cities, etc. It's all about this thing called complexity. It's actually a scientific term where there are many characteristics about what makes something complex in this scientific understanding. It's not just there are many parts, moving parts, all interacting with each other. It's also that the interactions are non-linear. It's the idea is that there are like a small little, non-linear means this power that we see, for example, in the power law, right? The fact that in the power law we have this exponent 6, right, for Bitcoin. It makes in such way where a small little change, like in this case time, creates a big change in price, right? So that will qualify as a non-linear system. And many of these complex systems are very, very much non-linear. And that makes them interesting because, something little changes, you see this big change, there are all these interactions, you will think almost that it's impossible to understand from a mathematical point of view. This is why many people say, you cannot use mathematics to understand society, right? I don't know why they never mention life, or maybe they even think that life cannot be described because they are not up to date with the research, but we are doing it. We are going more and more, because this is what changes, even like in biology. Biology is a science, but if you take it by itself, right, without like many biology books, you open the book, they tell you, they are very descriptive. They will give you, the different classification of the animals. They will tell you maybe how certain processes happen, but it will be more like reading a story, right? Then the physicists come. It's not that there are biologists that are kind of in between. There are a little bit like a physicist, a little bit like a mathematician, and they know a lot of biology. How do you call it, somebody like that? A biophysicist, you know? Yes, this is probably how you call it, because it's an expert in both fields. And then they bring these quantitative methods that are typical of physics. That is the critical thing. That is also what I'm trying to do with Bitcoin. I'm bringing this method from physics that, where to us, is like, for example, what is different with TA, right? Many people say that are not aware of in my work. They say, "Oh, I don't care about TA. I'm not doing TA. TA is like, oh, okay, it's very qualitative, right? This two-line cross, and maybe this is going to happen. We don't do anything like that. We want to quantify, even if there is two-line crossing. Okay, many times this two-line cross, and they created this event. Can I calculate the stats, right? Does it work 60% of the time, 70% of the time? And in fact, some people, some physicists or mathematicians did that with TA stuff, and they say, okay, you say there is a golden cross, right? When the golden cross has this thing happen, you call it golden cross, whatever it means, something else happens. Okay, can we show it? And they look at many data, and they found out they don't work more than 50%. It is basically chance, So this is what we do differently. We try to quantify, describe, does it work, doesn't work, is it more than chance, So the entire idea of bringing quantification, in this case, quantification means you measure stuff, right? Is why we have price, time, hash rate, things that we measure. We can measure somehow, right? We don't need it with hash rate. There is some way of measuring the hash rate in the machines, and in the entire system with price, it's recorded. It can be daily price or whatever, and mathematizable. So what does it mean here? It means that you can calculate, you can add, subtract. So once you have quantity like this, then you can also manipulate them. You can multiply them. You can take the power, right? Take the power of time. Many people told me, in particular economics people, that told me, you cannot take the log of time. Sure, I can take the log of time. What stops me to do that? And sometimes I even divide by zero. So like, why do you want? Maybe I get some crazy result if I do that, but you can do it, right? You can take once, if you have a quantity, you can, and you know what you're doing. There are units. Many times, like for example, when we do Bitcoin, we say price equal time square. I had people telling me, "Oh, it doesn't work. It doesn't mean anything because price is measured in dollar, time is measured in days, seconds, whatever you want to measure. The two are different. How can they be equal? You're saying they are equal." And I get surprised with many times when people ask things like that. Well, there is that unit with the quantity A, that is, in our case is 10 to the minus 17, has some units. That units will be, we usually don't write them down, but it will be, because basically we have 6, that this day will be days to the 6, so the days cancels, right? Because we want to be left with dollars. Dollars divide days to the 6, right? That will be the units of this weird constant. So, everything, you are able to go from price to dollars, right? And so you need to understand, you will have units because you're measuring things. We are measuring things in dollars. We are measuring things in seconds, years, if you're dealing with time. And then if you know how to manipulate units and how to simplify, it's called dimensional analysis. You simplify the units, the units. Sometimes when you take ratios between things, the unit disappear, and you can calculate, right? You can take the power, so you can take the log, you can do all these things with this quantity. And this is what we're trying to do in these different fields. Like, it's very typical of physics, and the idea of bringing physics to these different fields, because this is what it's trying to discuss. It's trying to, in the book, we are trying to create like an introduction to this idea that, people know that we do this in physics all the time. They are used, right? And by the way, even in physics, people were not used. This is why it was a scientific revolution. If you went to the wisest man on earth in the Middle Ages, or even before, you went to talk with Socrates, you went to talk with Aristotle, Plato, and you say, okay, if I drop an object, a stone, and the stone is moving, how fast after a second? First of all, they didn't know second, but let's say that they had some very small fraction of time, or they had some clocks, that water clocks and things like that. This is what Galileo was using, by the way. They didn't have, sophisticated watch, but they had sand watches, water watches. They probably could come close to something like a second, or at least think about it. Or, like a minute, after a minute, right? Minute means a small little thing, little minute things, right? This is what minute means. Minute of time, a small little fraction of time. After a minute, how fast the object is going. They had no clue. In fact, they will have thought that you are weird. Why we are asking me something like this about math? Because mostly we associated math with, geometry, like drawing triangles, and so we knew that kind of stuff. But if you had to apply to something like the motion of an object, they will say, you cannot use math to understand nature. It's not mathematical. It's sure it falls down, but, kind of, you cannot read. They didn't even think about the talk, because otherwise somebody will have done it. And for hundreds of years, they didn't. So when people say we cannot use math to understand society and human beings, they don't realize that they were having the same attitude that people had in the ancient times towards things that we know we can use math, like they're describing how fast an object is falling down. We have equations for that. At that time, they thought you were going to ask a very weird question. It would have been very interesting to have that conversation. Maybe I can ask an AI to pretend. It will be an interesting. That is the other thing I want to do at a certain point. I want to have we can bring in AI, like Chpt, and ask questions, and we can have a convo with Chpt and see what to say. You can say, hey, pretend to be a person, like a philosopher in ancient time, and I ask you this question: how will you react? And I tell you, they will, if it was a good impression, they will be surprised that I'm even asking this question, because they'll say, "Oh, you cannot really use math to describe that kind of stuff." So, but that is what the scientific revolution was about. Somehow, the time was ready. Of course, it was gradual. We were, a lot of, where it came from, a lot from the artisan, like Galileo, that was one of the fathers of science. He will go often to the shipyard. He had a lot of connections with engineers. People were building cathedral. People were building ship. Very practical people. They use their hands, and they use rulers. To do anything. To make a good ship, to make a good cathedral, they need to measure things. How big this thing is, how heavy it is, and they were very practical. For them, it was not a philosophy; it was like a real practical thing that they were doing every day, and it got a lot of inspiration, ideas from that. To say, why don't we use that approach to actually understand nature, understand why things move, how fast they move? And he started to do all these experiments, like let's drop a ball on a plane and see how fast it goes. And it was really, really clever, amazing. One time, what happened? I tell you the story, and then we can conclude. I don't remember what happened. It was not COVID, because we didn't have COVID, but we had some crisis, right? I think we had an hurricane, because I was teaching in Louisiana, and we have. It's not like Florida, but once in a while, like Katrina, we had an hurricane going through our city where I was teaching, and so we had to leave a university, all the equipment, and at a certain point we started to teach in these trailers, and we didn't have a lot with us, so we had to improvise. So I started to create a lab, but it was like probably like Galileo. Instead of having all these lasers, that measure the speed of a ball, I had to use like little bells, that exactly like Galileo will do, and drop these balls and measure the sound, like, oh, look, you see it happened. I had to do like very primitive things, and I appreciated, like, whoa, these people were amazing. Imagine we still had stopwatches. Imagine if I had a sand watch, to measure the time. It's like incredible, right? Like we have owed so much to these geniuses, of the old times. And Galileo was one of them. And he had this famous sentence where he said, nature is like a book that you can read, right? Because at that time, the Catholic Church didn't even allow you to read the Bible. This is why it was very controversial. They had to interpret. It was so centralized that the church told you what the Bible meant. So imagine somebody say, "Oh, actually, nature that was created by God is what we live at the time." Is written, it's a book, right, that you can read. Forget just the Bible, you can read anything, even nature, and you are allowed, because verify, do not trust, verify. This is what science is all about. And the nature book is written in the language of mathematics. So if you want to understand it, learn mathematics. And this is what we are trying to do in physics, but we are trying to convince the other fields. There is some resistance, because probably a lot of the people, they went to biology where people that didn't like math, they say, now you guys are coming here to our field, and you're disturbing us and you're bringing this crazy mathematics to describe biology. They actually resisted. West actually has stories where they didn't, they made a lot of problems to him to publish articles in biology. They were resisting him, they were criticizing him, but eventually, science is science. If you are saying something true and you can prove it, you win. And so he took some resistance. There was some resistance, but eventually he was able to move in that direction. And then, so this is, see what he say here, that in a certain sense, we will like, this will kind of a dream for physicists to find some kind of laws, maybe just not one, but laws that describe life, right? With different patterns, different. And what do we mean for laws? Because you remember when that crazy, silly debate with British Old, he was making a big deal about this law, power law. In science and in physics particularly, we mean a pattern, but it's not just some pattern, in the sky, some cloud. It's like a pattern that is very strong, very statistically strong, that tends to repeat. It's not that it cannot ever violate it, because there are laws and laws, like the laws of gravity. If we see a violation of the laws of gravity, that will be a big deal, right? What is going on? We never saw it before. But even with gravity, it's mostly like a statistical pattern, something that it seems is never violated, but there is no reason that maybe in some weird instance, in some weird corner of a universe, there is something going on that we don't know yet, that is an exception, and the law of gravity doesn't work. Even the law of gravity as we know it, for example, what Newton described, had to be revised eventually, because we needed to modify to describe very extreme cases of gravity where what Newton say it happened was not true. We had to extend it. It's not that. So basically, the way it works in that case is that Newton laws is a particular case under certain circumstances when gravity is weak of something much more universal and much more general that is called general relativity. General relativity of Einstein is the real way of understanding gravity that right now, and Newton's understanding, basically, right, one mass attracts the other, divided by r square. That simplification, it's a particular case that works pretty well when gravity is weak. You don't have to worry all the different complications that general relativity brings in. And if one day we extend general relativity to include even more exotic phenomena, right now, for example, we don't know how to make it work with quantum mechanics, and somebody comes and finds even more general theory, then we will have to modify relativity to include this new understanding. But this, can we do the same thing with life, right? Can we find patterns that are very strong, very predictive? Because that is the other thing, right, that people do not get, that science is about prediction. That this is why we study things, because we want to see these patterns, and then we want to see if these patterns are so predictable and they can extend it from the past to the future. That is another thing that I hear all the time, people saying, people that maybe don't have a lot of science a background, they say, oh, the past doesn't predict the future. What else should predict the future? And it does in many circumstances. When you cross the street, you look left, you look right, and you know that usually that means you're not going to be hit by a car. Imagine if we live in a universe like, Looney Tunes, where you look left, you look right, then you do a step and the train comes, right? Like in some these Looney Tunes, funny cartoons where something unexpected makes you laugh, right? Because it's unexpected. But imagine you lived in a universe like that, right? Or you run, you get out of a cliff, and you continue to run, right? Do you remember some of this crazy scene? They run, they continue to run, and they don't fall, and then they realize that there is nothing underneath them, and they fall, right? Well, the work doesn't work like that. We know, and this is why we can make prediction. That looks silly because the prediction is if I start to run in emptiness, I fall immediately after there is nothing under my feet. That is what you're expecting. You're making a prediction about the world. We make predictions all the time, both at a physical level, but also at a social level. Right? You say something that is offensive, that probably the person will react, right? We do that all the time. So I don't understand why people say something like that. Probably, what they mean. They mean with assets, with investments, it's very difficult. There is so much noise, and it seems so irregular and so random that it's very difficult to look at that and say, oh, I can make a prediction. This is probably what they mean. But even there, we can find patterns. This is why the power law in Bitcoin is a big deal, because we are saying that pattern is something that we have reasons. And as we explore this idea of scaling, you will see if there is something that scales up in a very precise fashion, it tends to continue to scale up in that way. It did it before, and it grew in that way over many orders of magnitude, exactly because there is some kind of mechanism that makes it behave in that way. And probably that behavior will continue. This is why we have a special name for this system that we call them scale invariant. That means the scale doesn't change. Or in this case, the scale growth, how the scale grows, it doesn't change, and it's very unlikely. And this is why you can use it to make predictions. And scaling is one of the best way of making prediction. And so, they introduce the idea, can we do this? Right? We are asking it almost like a question. And then you will see, we can continue next Thursday as we explore the book, that, the answer is yes. Now, can we do with everything, every single little aspect of biology? Maybe one day, and AI maybe will help us with that, where basically we have an equation for almost everything, like how the DNA works, etc. And if it is not an equation, one single equation, it's a bunch of equations. And then, if you can do a simulation, many of the simulations that you see of how atoms work, they are based on equation. They run the equations. So at least maybe like if it is not an equation, because many times if you don't find an equation, at least an algorithm, that is the second best to having a real equation. You have an algorithm and say, okay, this happened, then this happened, and so on. And you can run that algorithm. But that is kind of what we are trying to do. Now, if there is like a single simple equation that is, oh, life is this, very unlikely, because it's so complex that we are very unlikely finding one single equation or maybe 5 equations. But, think about one of the things we will explore will be that metabolic equation that I show you many times, right, with Kleber's law. That is amazing already, right? There are all these different animals, and we can tell by the size of an animal much energy they use. That is one of the fundamental things we'd say, right? How much energy. But life is all about processing energy, right? Using energy, because, you are eating. Why you are eating? Because food has energy. You are taking this food. It's two things, right? Energy from the food, but also new components, right? Because we substitute, we change, we we need proteins, we need to make different things because we are healing and recycling all the material in our body. But that is the two function of why you're getting energy. And by the way, anybody knows where basically almost all the energy from our food comes from? Anybody has an idea about where the energy comes from in our planet? Like almost everything. Like I can try to think some exception, but almost all the energy from the food comes from the sun, right? Because if you're thinking the plant are taking the light from the sun and we are making energy out of it, right? Mostly in the form of sugars, right? And then there is energy also in proteins, etc. But it's mostly this process of going from the light of the sun to things that they can be used to store the energy, like sugar, proteins, and things like that. And then we eat, the predators eat the plants. Well, predators, the herbivore eats the plant, and then the predators eats the animal, they eat the plant, right? And this is how we get our energy. But in the end, it comes from the sun. That is really cool, right? And can we write equation? Like, for example, when we discuss the Kleber's law, we find a pattern. There is a law. Is many of these laws that he's hinting here are going to be, guess what? Power laws. Because that is one of the things that we found, that many of these patterns that we are looking for explaining the regularities of life, and there are regularities, are power laws. And there are many of them. And so this is what the book is trying to prepare, this idea that there is scale, that we are looking for regularities, patterns, almost like we do with physics. And then we found them. We found a lot of them. It's not that everything is a power law, right? But a lot of these patterns are power law, because this book is focusing on understanding scaling phenomena, and power law are one-to-one, right? That is like the most important fundamental principle of a power law. This is why we make a big deal. It's not just like any other pattern that Bitcoin has. It's like these things, it's these like organisms and planets, etc. It's like one of these systems where power laws are so important because of all these amazing, beautiful properties that we want to study in this book. Anyway, I can try to answer some questions. You're asking to join the Patreon. Will you indicate or tell me when we have top, and will you be given ideas how to make money during the bear market? Yes. So part of what we do with these indicators, because we say this is the science, and we'd like you to understand the science, appreciate the science, also because it's beautiful, right? And beyond being practical. But we are still coming here because you guys are interested in Bitcoin, and we want to be wealthy and escape the matrix, etc. And knowledge is power, right? And the indicators are all about how to use this knowledge. And so yes, we try to tell us when we have. This is why we have right now, I think, 8 indicators, and we use them together to identify the tops, the bottoms. Plus, the idea, when you join the Patreon, you also join a community. We are about 600-700 of us, and we talk on the Discord channel. We have different Discord channel. We have different ideas, different strategies. We discuss this strategy. Right now, we have many different ways. Like, right now we're talking about having options, for example. So you don't have to sell your Bitcoin. You could open, you can buy puts option, against the MicroStrategies, maybe against the ETFs. And so there are many different things that, like the bear market, we could make money using this strategy. So, because in the end, science is beautiful, but technology, it's even more, not more, but it's one of the things that makes this knowledge, just from being beautiful and this interesting, actually practical. So you can combine both, right? So that, and then Makoto is asking about this magic number 4. So what happens when you find, so the power laws, are one of the things that we find in nature that are related to this scaling, right? Because, and we will explain better why what a power law has anything to do with scaling. I can give you a preview. Basically, you are taking the log, and the log is a way of extracting the scale, because it gives you basically, if you write a number as 100, so 10 to the 2, it gives you 2. If you write it as 1,000, it gives you 3. So it focuses on the scale. It gives you a scale. So you're writing down, like what you do with Bitcoin, you write the scale of a price, the scale of a time, and then you see a very strong regularity. What is that regularity? A line. If you see a line is such a regular thing that our eyes immediately recognize it. Oh, wow, there is something that changes in a very regular fashion, right? Because what a line is, a line says there are two quantities that are related in a proportional fashion, right? But what is proportional there? It's not the price itself, it's not the time itself, it's the scale. So the scale of price and the scale of time are growing in a very regular fashion. It is described by this line. And that makes the system scale invariant. Because at any scale, you cannot say, what is the typical scale? For example, you could not say, if somebody attempts to do that, they will do a mistake. And that is, again, another thing you learn about the scaling idea. If somebody says the average price of Bitcoin over its entire history, you could do it. You could take every single price, you add them together, divide by the number of days, that you use to do the calculation, and then that number, by definition, is an average. So it's not that you cannot do it, but that number will mean nothing, because usually it means something when you have something that looks like a bell curve. Then that number represents the most likely value. But with Bitcoin, that doesn't mean anything, because in particular, it has a scale invariant behavior. And when you have a scale invariant behavior, there is not an average. There is not an average behavior. The line is kind of close to what you can think like the average behavior, the scaling behavior. But again, it's kind of a process more than being just a single number. And so one of the things that we do when we found these power laws is to measure the slope of that line. And in the case of Bitcoin, it's 6. And then, okay, great. Okay, I found a power law. I'm so happy. Then what? Because with science, it's always like that, right? I'm sorry, I'm going to drink a little bit. It's not whiskey. I wish it was whiskey. It's just water. So, we never stop. It's a never-ending adventure, So the next step is, okay, where the heck that 6 come from? What does it mean? Where does it come from? And if you read my work, I don't know, because many people are not familiar with all my work. That is something that, by the way, I need to do more videos. Maybe I should do a series of video where I break down all the different discoveries that I did on Bitcoin. But I know where it comes from. In the beginning, I didn't know. I was banging my head against the wall. And then I found out it comes from the addresses, addresses is a power law, of in time, with the cube of time, and the price reacts to the addresses with the square, and you combine, you get to 6. Now, these 4 that you are mentioning, it's something that we will see in this chapter, because one of the laws that is mentioned is called the Kleber's law. So the Kleber's law, and I'm going to write in the chat so you can see, the Kleber's law basically says something like the metabolism, so the energy that the animal is consuming, is proportional. And I write it as a proportion because there is always some constant that is kind of a link between one quantity and another. It has all the units, but also it's a proportionality constant. But it's less important than the two quantities and how they are relating. Their power laws is always some kind of a power. So it will be the size of an animal, in this case, the mass of the animal, to the power of 3/4. Okay, so this is how it is. This is called the Kleber's law. Kleber's law. And I think it was discovered in the 30s or something. And then we will study it. We will see a graph and describe it. But you can try to make sense, because basically it says as the animal grows and becomes bigger and bigger, the energy that he needs is not, you will think it's linear, like you will think, okay, I double the size of the animal, I need 2 times more energy, because you're kind of doubling. We physics, we have this joke of a spherical cow. I don't know if you ever heard. Yeah, because we try to simplify things. So if I have an animal, let's make it like a sphere or maybe a cube, but because I don't want to deal with the limbs and the here, it's too complicated. Let's approximate it, because in physics we like this approximation. Let's make it like a sphere. It sounds funny, right? With a sphere, like many times, like you will go in a physics class, I will say, let's assume spherical something, uh, and then in this case, if you're studying an animal, it would be a spherical cow, right? That is really, I don't know, it's like a nerdy joke. But if it is spherical, if it is like roughly volume, you double the size of a sphere and you get 2 times more mass, right? You're doubling the mass, not the size, because in that case it will go. So I say something wrong. So you double the size in terms, no size in this case, not in the radius of a sphere, but the mass, right? So if you double the mass of the object, you will get roughly 2 times the number of cells, right? And then you will think, well, there are 2 times the cells, we are going to consume 2 times the energy. And instead, no, something else happens. What happens is that you do 2 times. So if I do 2/3, we can even calculate it, right? You double the mass, you do 2/3. I can go to my calculator. If you guys want to follow along, you can also do it. This is how you do it. Even with Bitcoin, if you want to know how much more Bitcoin you get, how much more money you get in 15 years, because you're doubling the life of Bitcoin, you take 2 to the 6 and you get 65. So you get 65 more value of your Bitcoin. But in this case, we are saying let's double the mass of the animal. How much the energy consumed by an animal is. And what do I get is 1.68. So basically kind of 1.7 close. That means instead of 2 times the energy, you get a discount of 30%. Imagine I go all the way to 10, so that will give me, let me write it here, 1.67. So there is a discount. So now if I go to 10 and they make my animal 10 times bigger, the discount will be much bigger. So we can calculate it, right? So if I say 10⁵, like there are animals that are 10 times bigger than another, right? Very easily. That case, it's only 5.6, right? So you see, look, I got almost a 50% discount, right? Like a really big discount in how much energy I need. And we will explore that in the next, but just because you asked the question, where that four num comes from. Because initially, if you try to find an explanation, you will think, maybe the explanation is that there are vessels in the body that brings the food to different tissues, and that will go with kind of a square, because a vessel, the cross section, right? Imagine you have a pipe and you cut it. The cross section is a surface, like a circle, and that surface, it goes with the square, because this how surface go, right? The dimension of a surface is a square, and then we have to distribute the food over a volume, and volume goes with the cube. So you will expect that exponent will be more like 2/3, and it's not. It's like 3/4. So where does it come from? Is this reasoning about the size of vessels and the mass kind of wrong? Am I going in the wrong direction? And it turns out that is not. in fact, you are going in the right direction. It does have to do with vessels and masses, etc. But you kind of didn't consider one thing that is almost like a spoiler. I don't know if I should say, but it turns out this has to do with the complexity of a circulatory system. It's so intricate. It's so, you know, is made by so many different little parts. You know, the little vessels go down and they become capillary, and this capillary, you know, have you ever seen these shows? I think some person in China, yeah, it has to do with fractal dimension. He takes the human body and makes it like basically a process that looks almost like plastic. Then he can preserve this body, and he has this incredible, beautiful display. They are a little bit grotesque, right? Because these were real human beings, I think prisoners in China or whatever. But you can see all these intricate vessels and etc. And it looks like a fractal, right? This idea of fractal is something that it looks like itself, self-similar at many different scales. And so it's a very strongly related concept to scaling, that the power law is kind of causing. So it's not exactly the same. You cannot say the power law it's a fractal, but it does have fractal like properties. And so they are related concepts. The idea that when you have something that's kind of self-similar at many different scales, then it's almost like you're going in another dimension. And so that 4 comes from 4 dimension. In a certain sense, human beings are actually almost 4-dimensional beings. Not exactly, but because the complexity of our nervous system, because something very similar happened with the nervous system, of a circulatory system, it gives us almost like 4-dimensional properties, you know. And so this is where that core 4 comes from. That is more complicated than we thought initially, and so this is why you have that 4 kind of cripples out, you know, from how this organization over many different animals is structured. You know, that you need to consider also this more complex aspect of human physiology or animal physiology. And it's fascinating, you know, because talk about going down the rabbit hole, you know, it's really deep, incredible rabbit hole. And this is how you discover things. The same thing with the power law in Bitcoin, you know, this is why probably I need a like different video to explain all the things I explore. I didn't stop with that straight line. I'm going to the rabbit hole deeper and deeper and deeper. I found so many different other properties about Bitcoin, all indicating that it is exactly like that. It's like one of these scaling phenomena where there are so many fascinating things that are happening that most people don't know and that are not aware, but they are there because Bitcoin is a complex system and it's a scaling system. So, you know, this is why this book is so relevant, you know, for what we want to know, that is mostly Bitcoin, because imagine you're mostly Bitcoiners, and that, you know, it's fascinating by itself to study all this stuff, but then it's really cool to look at the connection with Bitcoin, you know. So hopefully it's something useful for all of you. But anyway, yeah, let's chat. If you want to join, did you say you were okay? You know, we do have this Patreon program where you can join our Discord and we can have conversation. But you can come to these meetings. I'm going to have this meeting every Thursday, and so we make them more public. You don't have to be part of a Discord group. There are some Discord group people, but we do so many other things there, and I'm going to make this more public so everybody can participate. And so you can ask, we can discuss this in the other meetings, okay? And feel free always to contact me. This is what I do. That is my job, my self-appointed job, to be an educator, being a science communicator. So I really love it and I enjoy it. And I'm actually thank you to come and spend this time with me, guys, wherever people are there looking at this video. I really enjoyed. And let's continue to do this, right? I will be here every Thursday at 4 p.m. PST. So we are going, and this is the beginning of chapter 3, if you want to catch up. So if you want to read the book with me, we will continue. This is in my version is page 81. So this is where we are. It's the Kindle version. So if you want to catch up to page 81, then we go ahead and we will continue. All right. Thank you so much, guys. See you soon. Bye.